Hey guys, this lesson's on finding a electric field at a point in space due to two dipoles. So I have a problem here, and uh, this is basically it. We have a dipole here, positive, negative, and a dipole here, positive, negative. And we want to find the electric field at point A. And we have these values. S is our distance between our dipoles. It's going to be 0.01 meters. Our distance from the dipole to A and this dipole to A, which happen to be the same distance, is going to be 0.05 meters. And Q, which is going to be our charges, our absolute value of charges of each one of our dipoles, is going to be 2 nanocoulombs. So with that, let's get started. So let's remember our dipole equations real quick. So our electric field perpendicular of a dipole equals 1 over 4 pi epsilon naught times q s over r cubed. And our parallel, I'll just write this down here, equals basically the same thing except for times 2, but I'll write it down anyway. 4 times pi epsilon naught q s times 2 over r cubed. Okay, so let's kind of break this up and do it in two parts. So let's first start with this this dipole here and find the electric field of it due to that, and then we'll find it for this. So this is parallel to it. So let's plug in the units. E parallel is going to equal 9 e to the negative 9th, because remember this constant is always this. Newtons meters squared per coulomb squared. Our Q is 2 nanocoulombs, which we have to convert to coulombs. So it's going to be 2e to the negative 9th coulombs times s, our distance between the two dipoles, which in this case is 0.01 meters, and times 2, just because that's part of the formula. And all of that over r cubed. And in this case, r cubed is 0.05 meters. 0.05 meters cubed. Okay, so once you calculate that all out, you'll get 2,880 newtons per coulomb, which is a lot of electric field, but in this case it's okay. So this will be our electric field due to this. So again, let's use our superposition. So we know that negative pulls towards and positive pushes away. And since the negative is closer, it's going to have a stronger effect. So the electric field, this is going to be like this. Okay, so now let's do it for parallel. Perpendicular, sorry. Equals 1 over 4 pi epsilon naught times q s or r cubed. And again, since these are the same distances away, you could just naturally see that the answer to this is going to be this divided by 2. But again, let's just calculate it out so we can figure it out. So remember, this is the constant, 9e to the 9th, times q, which is 2e to the negative 9th coulombs. Because remember, we got to convert this to coulombs, times s, which is 0.01 meters, over 0.05 meters cubed. Okay, so I guess that's all equal to that. And that'll give us, once you calculate that all out, it'll equal 1,440 newtons per coulomb, which is, yeah, exactly half that. But now we have to find the direction. So again, let's look at superposition. So let's see, we know that negatives pull towards. So the electric field due to this negative is going to be this. And we know that positives push away, so the electric field due to this positive is going to be this. So our net electric field is going to be this. Okay, so now we have to find the net electric field due to this arrow, which is for the parallel, and then this arrow, which is for the perpendicular. And since they're going in opposite directions, they're going to be subtracted by each other. So we just do a simple math problem. So 2,880 minus 1,440. And that will equal 1,440. So when this is all said and done, this, since it's half of this, takes out about half of this. So the net electric field, let me write area over here, is going to equal 1,440 newtons per coulomb in the direction towards the parallel one. And that's how you figure out a problem with two dipoles and finding a point in space. So if you have any more questions of this, please send me a line and I'll get back to you as quick as I can. I'll see you next lesson.